Welcome to a new chapter, Chapter 5 on eigenvalues and eigenvectors. Today we're going to talk about eigenvalues, eigenvectors, and define them. They have a rich history. D'Alembert used eigenvectors to solve problems involving a weighted string, and he had a system of 3 differential equations which he was solving, and eigenvalues and eigenvectors weren't called that at the time. In fact, we didn't even have matrices at the time, but he did use a form of those to solve his problem. Cauchy, a generation later, used eigenvalues and eigenvectors to rotate the axes so he could write a quadratic equation without the middle term. So for example, an ellipse could be written x squared over a squared plus y squared over b squared equals 1 with no middle term. Euler had done that earlier. Euler was a contemporary of D'Alembert, but Cauchy formalized it and also generalized it to any quadratic surface. All right, enough of that. This clip here, this is just from a movie I saw in the 80s. It's kind of cheesy, but in the clip they talk about a problem not being solved because of the eigenvectors weren't right, or the eigenvalues. I don't remember which. It's kind of funny. Okay, what are eigenvalues and eigenvectors? When you take a matrix and you multiply by a vector, you get another vector. So ax equals lambda x. Well, ax equals another vector. If that vector is of the form lambda x, so if ax is a multiple of x, if they lie on the same line geometrically, then you have what's called an eigenvector-eigenvalue pair. X is an eigenvector corresponding to the eigenvalue lambda. It's important that x is non-zero. Eigenvectors cannot be zero. Non-zero. Eigenvalues can be zero. So let me just show you a picture here. So here's a vector x in red, and then ax is in green. So you can see that here, this vector x is not an eigenvector for a, because ax and x don't lie on the same line. But as I go around there, I can see that ax lines up with x. And actually they have the same length, which isn't that common. But here, no eigenvector, none, none, none. And then here we have lining up again right there. So x would be an eigenvector for a because x and ax lie on the same line. We'll see on the next page, while I'm here, that some matrices do not have any real eigenvectors. For example, the matrix that rotates 90 degrees about the origin, ax equals lambda x, you can see here ax and lambda x, x and ax will never line up on the same line because a rotates x by 90 degrees. So it just chases around the circle there and they never line up. They do, by the way, have complex eigenvectors and eigenvalues, but that's for another course. All right, back to our lecture notes. So let's do some concrete examples. Suppose A is this matrix, is V an eigenvector? So we want to answer the question, is AV equal to lambda V for some lambda? If it is, then the answer is yes. So AV is equal to, let's see, -2 and then +6. So is that a multiple of -1, 1? Well, if it were a multiple for the first part, the multiple would have to be 2, but that doesn't work because 6 is not twice 1. So this is not lambda -1, 1 for any lambda. So the answer is no. All right, now you try it. Show that U is an eigenvector of A and find a corresponding eigenvalue. So pause it and give it a shot. Okay, AU is 0, -2, -4, 2 times 1, 1. And that's equal to -2, -2. And that is equal to -2 times 1, 1. So yes, 1, 1 is an eigenvector, and the eigenvalue is lambda equal to -2. And what we would say is that 1, 1 is an eigenvector for A with corresponding eigenvalue lambda equal to -2. So they're a pair. Eigenvector gets paired with an eigenvalue. Okay, this is the one I mentioned earlier. The rotation matrix has no real eigenvectors. And now let's ask a more difficult question. So the question above was, given a vector, is it an eigenvector? Now, given a number, is it an eigenvalue? So that's a harder question, and I'm going to walk you through how we're going to solve that. Lambda equals 2 would be an eigenvalue if and only if ax equals 2x for some non-zero x. So it has a non-trivial solution, means x is non-zero. So it has there's some x out there that's not the zero vector for which this is true. So let's rewrite this. Let's move the 2x over. So this is the equivalent to ax minus 2x equals 0, has a non-trivial solution. Now I want to pull out the x, but I can't write, if I pull out the x, a minus 2 times x makes no sense. You can't subtract a number from a matrix. So what I do is I put in an I there, the identity matrix. You can subtract a and 2i because they're both matrices of the same size. Of course, you would use the identity that's the same size as a. So now this is equivalent to a minus 2i times x has a non-trivial solution. Well, we can solve that. We're just going to reduce the augmented matrix a minus 2i, augmented with the zero vector. So when we do that, let me just show you. You'll be able to compute a minus lambda I in your head very soon, but here's how to do it. When you take a matrix and subtract, in this case 2i, 2 times the identity just puts 2's on the main diagonal. And so what you end up doing is subtracting 2 on the main diagonal from A. And so I end up with this matrix 1, 2, 3, 6. So that's the one I want to reduce, augmented with 0. And I went ahead and did that because it only took one operation. All right, and so now where I am is I've got two variables, x1 and x2. x2 does not correspond to a pivot, so x2 is free. x1 is -2 times x2, so -2t. So solutions look like t times -2, 1. So any t not equal to 0 will give us an eigenvector. Will give an eigenvector. So eigenvectors are not unique. Lambda equals 2 has infinitely many eigenvectors. Any t will give us an eigenvector. So let's take t equal to 1. Because we were asked to find a 1 corresponding eigenvector, not all of them. So if we just want 1, let's let v equal to -2, 1. We can check our work. The check would be to compute AV. It should be 2v. So AV is 3, 2, 3, 8. And I'm multiplying by -2, 1. And so I get, when I dot, -6 plus 2 is -4. And then -6 plus 8 is 2. And yes, indeed, that is twice -2, 1. So I'm done. All right, practice. Lambda equals 1 is lambda equal to 1 an eigenvalue for A? I can tell you right now the answer is going to be yes. If so, which it is, find one corresponding eigenvector. So you're going to solve this exactly the way I did solve the other one before. You want ax to equal x because lambda is equal to 1. And so you want to solve a minus I times x equals 0. All right, so pause, do it, come back. All right, so hopefully you did that. A minus I is equal to, I'm just going to subtract the identity off the main diagonal. So 4, 0, 2, 0. So we want to reduce A minus I augmented with 0. 4, 0, 2, 0, 0, 0. I can do a bunch of things at once. Multiply row 1 by -1/2 and add it to row 2, and that will kill off row 2. It'll be all zeros. And then divide row 1 by 4. So we'll finally get 1, 0, 0, 0, 0, 0. All right, that's consistent. So we do know that 1 is an eigenvalue. X2 is free, and x1 is not free. It's 0 because that top equation reads x1 is 0. So solutions look like t times 0, 1. So we'll take t equal to 1, v equal to 0, 1 is an eigenvector. So the answer is yes, because this system is consistent, and here's our eigenvector. Okay, so let's summarize some things. And this will be, again, drilled into you in the next section. And when I say drilled into you, we're going to make it more formal. But to see if a given vector is an eigenvector, it's super easy. Just check if AV is lambda V for some lambda. All right, multiply A times V. If it's a multiple of V, you're good to go. To find any single eigenvector corresponding to a lambda that's given to you, like the example above where I say lambda equals 2, is that an eigenvalue? Oh, I guess I was asking a question up here. Is lambda equal to an eigenvalue? If so, I would want to answer this question. When I get to this, I see I have a consistent system, so I would say yes, and then go on with the rest of my solution. But going back to what we're looking at, if you're given lambda, what you want to do is solve a minus lambda I times x equals 0 by reducing a minus lambda I augmented with 0. If that's consistent and you have a solution, a non-zero solution, then any non-zero x will be an eigenvector. And finally, this we'll talk about more in the next section, but how do you find eigenvalues? The lambdas were given to us in the examples above, but what if I gave you a matrix and said, find the eigenvalues? Well, the eigenvalues are the non-zero x's for which this has a solution. Sorry, the eigenvectors are the non-zero x's for which this has a solution. So if you're looking for the lambdas for which this has a non-zero solution, by the IMT, a minus lambda I times x equals 0 has non-trivial solutions if and only if the determinant of that matrix is 0. Determinant a minus lambda I equals 0. And I have the IMT on one of these pages. Let me just show you that. Ax equals 0 has only the trivial solution is equivalent to determinant A not equal to 0. That means if the determinant of a matrix is 0, then that matrix times x equals 0 will have non-trivial solutions. So we're using the negation of the IMT. And we'll do more practice finding eigenvalues next time by solving what's called the characteristic equation. This time we're not going to do much of that. Only one example will require that. All right, let's talk about bases for eigenspaces. What is an eigenspace? It's the set of, if you have a matrix A, and A has corresponding eigenvalue lambda, the eigenspace for lambda is the set of all x such that Ax equals lambda x. That's the set of all x such that A minus lambda I times x equals 0. So that's just the null space of A minus lambda I. Okay, so an eigenspace is a null space. It's a set of all x such that A minus lambda I times x is 0. And that's the null space. So to remember, eigenvectors can't be 0. So if you take the null space, that includes the 0 vector. So the eigenspace is the set of all eigenvectors also with the 0 vector tossed in. So to find a basis for the eigenspace, we know how to find a basis for a null space. So that's all we have to do. To find a basis for the eigenspace corresponding to lambda, find a basis for the null space of A minus lambda I. Okay, this sounds worse than it is. Trust me, by the next section, this will not be as frightening, and it will not seem so like it's just so foreign. Let's do an example. Find a basis for the eigenspace of A corresponding to the eigenvalue 2. All right, so we want to find a basis for the null space of A minus 2I. All right, so I took A here, and I've subtracted twice the identity, and I get this matrix here. And so if I want a basis for the null space, what I do is augment with 0 and reduce. And so you don't have to watch me do a calculation, so I already set that up. Here's A minus 2I augmented with 0. It only took like one step to reduce. And so here I am with the reduced matrix. And so let's go from here. We've got 3 variables. Let's start at the bottom. X3 does not correspond to a pivot, so that's free. X2 does not correspond to a pivot, so that's free. And X1 is not free. X1 is S plus T, X2 plus X3. So X bar equals S times 1, 1, 0 plus T times 1, 0, 1. So a basis for the null space we're going to pluck out this vector and this vector. They're linearly independent and they span 1, 0, 1. Okay, so I'm going to name these V1 and V2. And now you're going to pause and go ahead and find a basis for the eigenspace of A, same A, corresponding to lambda equals 4. And if you get stuck, the solution's at the end. All right, hopefully you did that because I'm not going to go through this one with you because I put the solution at the end. You need to do this one. But what you're going to get, I hope, is basis 0, 1, 1. Now I'm going to call this V3. And notice I'm naming them V1, V2, V3. And the reason I'm doing that is because I want to look at theorem 2 in the context of a concrete example. So theorem 2 says if you have a square matrix A, and if you have eigenvectors that correspond to distinct eigenvalues, then the set of those vectors is linearly independent. And so what that tells me is since V3 corresponds to lambda equals 4, And V1 and V2 correspond to lambda equals 2. Those are distinct eigenvalues. That would tell me that V1, if I paired V1 with V3, that would be a linearly independent set. And if I paired V2 with V3, it would be a linearly independent set, because each of these guys corresponds to distinct eigenvalues. But we can make the theorem better. And the better theorem is that if we have distinct eigenvalues, and we take a linearly independent set of eigenvectors corresponding to each of the eigenspaces, we can merge all the eigenvectors together into one set that's linearly independent. So that tells me if I take V1, V2, and V3, toss them together into a single set, it's linearly independent. So what I have actually is 3 vectors in R3 that's linearly independent. So they have to span. So V1, V2, V3 is actually a basis for R3. We'll look more at that later. All right, so now I'm going to talk about some properties of eigenvalues and eigenvectors and an updated IMT. So I'm going to go through these properties with examples to make them more clear, but just to read them off, if lambda is an eigenvalue of A, lambda to the n is an eigenvalue of A to the n. The eigenvalues of a triangular matrix are the entries on the main diagonal. A is invertible if and only if 0 is not an eigenvalue. So that is going to be the updated IMT. Number 3, let's just do that now. Let's jump to our IMT. Given that 3 is true, we can add our IMT, which is ever growing, gets one more entry. A is invertible if and only if 0 is not an eigenvalue of A. All right, so that was quick. Let's go back up here. If A is invertible and lambda is an eigenvalue of A, 1 over lambda is an eigenvalue of A inverse. And finally, A and A transpose have the same eigenvalues. Not eigenvectors, but same eigenvalues. And let's just start with 5, because I'm not going to even give an example of 5, but I'm just going to point out how you would solve it. I put the proof at the end, and I don't think much understanding is going to come from reading the proof, but you're welcome to do that. What you have to do is show that A and A transpose have the same characteristic equation, because the eigenvalues are the roots of the characteristic equation. And again, even if they have the same eigenvalues, that doesn't mean they have the same eigenvectors. All right, now let's go back to examples of these other properties. So for property 1, I'm just going to show you with A squared. So let lambda be an eigenvalue of A with corresponding eigenvector x. So what that means is AX equals lambda x. That's what that means. We're going to find A squared x, and we should see that lambda squared, so lambda squared should be an eigenvalue for A squared, according to property 1. But let's see, and let's see why it's true. So what I do, I take AX equals lambda x, that's given, multiply on the left both sides of that equation by A. So now on the left I have A squared x, and on the right I have A times lambda x. Well, lambda is a constant. Constants can come out of matrix multiplication. So that's the same as lambda times AX. But remember, what is AX? AX is lambda x. So that's lambda times lambda x, which is lambda squared x. Thus, lambda squared is an eigenvalue. I would just abbreviate that EV, except that eigenvector would have the same abbreviation. So lambda squared is an eigenvalue for A squared with the same eigenvector x that A has. So lambda squared is an eigenvalue for A squared, but it has the same eigenvector x as A. So that's interesting. This is the eigenvector for A. It's also an eigenvector for A squared, but its eigenvalue changes. Its eigenvalue isn't lambda. Its eigenvalue for the matrix A squared is lambda squared. Okay, next one. The eigenvalues of a triangular matrix are the entries on the main diagonal. So here's an example. We've got a triangular matrix here, upper triangular, so 0 is below the main diagonal. The eigenvalues are going to be the roots of the characteristic equation. And the characteristic equation is the determinant of A minus lambda I equals 0. That was property 3, the summary number 3 that I mentioned on the first or second page. So we want to solve determinant A minus lambda I equals 0. So what I did was I took A and I subtracted lambda on the main diagonal, because when you subtract lambda I, you're subtracting this matrix from A, and that just subtracts lambda on the main diagonal. So I did that, and then here, this is the notation for determinant. I want the determinant of that matrix. But we know from from properties of determinants, we know the determinant of a triangular matrix is the product of the main diagonal entries. So I can just write 2 minus lambda, 5 minus lambda, negative 7 minus lambda, because those are the diagonal entries. Multiply together, and that equals 0. So the roots are lambda equals 2, 5, and negative 7. Those were the entries on the main diagonal of the original matrix A. So that will be a real time saver later on. Okay, the next one is A is invertible if and only if 0 is not an eigenvalue. All right, A is invertible if and only if 0 is not an eigenvalue. We know from the IMT that A is invertible if and only if the determinant of A is not equal to 0. And so 0 not being an eigenvalue follows from this right here. When I write determinant A is not equal to 0, that's equivalent to determinant of A minus 0I is not equal to 0. Because when I subtract 0I, I still get A. So these are the same statement. Well, the one on the left says A is invertible because the determinant is not 0. And the one on the right says 0 is not an eigenvalue, because eigenvalues are the roots of the characteristic equation. And so if this is not 0, then I know that 0 is not an eigenvalue. All right. Next, we want to show that if A is invertible with eigenvalue lambda, then 1 over lambda is an eigenvalue for A inverse. So let's start with the fact that we have, if lambda is an eigenvalue for A, then AX equals lambda X for some non-zero X. Furthermore, since A is invertible, we know that lambda is not equal to 0. You might say, how do we know that? We know that from property 3. 0 is not an eigenvalue. Okay, now multiply both sides on the left by A inverse. A inverse AX equals A inverse lambda X. So on the left I have X, and on the right, pull out the lambda, I have lambda A inverse X. Now, since lambda is not equal to 0, I can divide by it. 1 over lambda X equals A inverse X. Well, that does it. If you read it backwards, A inverse X is 1 over lambda times X. So 1 over lambda is an eigenvalue for A inverse. And it has the same eigenvector as A, with the same eigenvector x as A. So it's got the same eigenvector that A has, but the eigenvalue is different. All right, and that is it. The updated IMT, and then we'll talk about finding eigenvalues and eigenvectors more in the next section.